I'd like to talk a little bit about what's called implicit differentiation. So first of all, I want to give a little definition. An implicit function is a function where y is not isolated. You don't really need to know these terms, but for the purpose of understanding implicit differentiation, I think it helps. So we do have some implicit functions that you can actually write in what we call explicit form. For example, if you have x times y equals 1, that starts off and y is not isolated, but you can actually rewrite that as y equals 1 over x. So we're not going to talk about that type of equation today because you actually know how to take the derivative of 1 over x. We are going to talk about the ones that cannot be written in explicit form, such as 2y squared plus 3xy equals 3. That type of thing, it's really, really hard to solve that for y. You can try it on your own if you want, but you're not going to be able to. So implicit differentiation is going to be used to find the derivative of things like the second one. And our little rule is that if you have terms with only x variables, you just differentiate them, take the derivative normally. For those with other variables, you are going to use the chain rule, and I will give you a bunch of examples. But before I give you some examples, I just want to make sure that you recognize this notation. I think we've used it a bunch of times, but if you see dy dx, this is the derivative of y with respect to x. Occasionally, you will see dy dt. In that case, you need t's in it in order to actually take the derivative. So be very cognizant of what your denominator of that dy dx or dy dt or whatever function that is. Make sure that you know what you're actually differentiating with respect to. Those are going to be the ones where you take the derivative normally. Any other variables other than that variable on the bottom, you are going to have to use the chain rule like I'm going to do right now. So I also want you to notice this notation here. Basically, this is saying the derivative of x to the fourth plus y to the fourth with respect to x. So we're differentiating with respect to x. What that means is that we treat the x variable, the x to the fourth, like we would any normal variable when we take the derivative. So that's just going to be 4x cubed. With our y variable, however, we need to treat that a little bit differently. So with the chain rule, we had the outside and the inside. And this y to the fourth, my inside is the y. My outside is the fourth power. So what I'm going to do is use the chain rule. I take the derivative of the outside portion of it, which is the fourth power. Derivative of something to the fourth is going to be 4, and then whatever's on the inside to the third. So I'm going to keep the inside the same. The inside is still going to be y. Then I multiply that by the derivative of the inside. Derivative of y, don't overthink it. It's not going to be 1, by the way, because we're taking the derivative in terms of x. Derivative of y in terms of x is going to be dy dx. So for the next one, I have the derivative in terms of t of v plus t plus 4. So with v, I actually don't have an inside or outside. I don't need to do the chain rule. That's just going to be dv dt. The derivative of t with respect to t, remember we have the same variable as what we have in our denominator, so that's just going to be 1. Derivative of 4 is a constant, so my answer for that one is actually just going to be 0, so this is my answer. For this third example, we're actually using the product rule. You're welcome to try it on your own if you want. You can pause if you'd like. So for this one, we use the product rule. We start by doing the first thing, which is x squared, times the derivative of the second thing. So derivative of y to the third, remember we use the chain rule. Derivative of something to the third power is going to be that thing squared. multiplied by the derivative of y with respect to x. So we write dy dx. Then we do plus the derivative of my first term, which is 2x, times the second one. So you'll notice we're only writing the dx dy or the dy dx when we're taking the derivative of something that has a y. So please just make sure that you remember your rules. Make sure that when you see a product, you're using the product rule. I'm going to tell you the number one wrong answer that people give me, and that's going to be this right here. They try to not bother using the product rule, but if you have a product of any two variables and you cannot simplify it, you have to use the product rule. So don't just take the derivative of each thing individually. So this next one, you might be looking at it and saying, isn't this the same thing that we just did? It's not. So we actually need to find our end result as something where you have dy dx equals something. So that's going to be our final goal here. Just make sure that you know what the problem is actually asking you for. So the way that we're going to do this, first thing that you probably want to do is check and make sure that you can't solve for y. You can't, by the way. What you're going to find if you try to solve for y is that you get a plus or minus. That means that it's not an explicit function, it's an implicit function. So what we're going to do is we're going to take the derivative with respect to x of this entire equation. So we write it usually like this. So then I'm just going to go ahead and take the derivative of each term individually. So the derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x is going to be 2y times dy dx. The derivative of 16 is 0. So I got my first step done. Now my last step is that I need to solve for dy dx. And you solve this just like you would solve any other equation. So I'm going to move over the 2x first of all. I get 2y times dy dx is equal to negative 2x. Next, I just need to divide both sides by 2y. So when I do that, I get dy dx is equal to negative 2x over 2y. So my final answer is negative x over y. We're going to do one more example, and we're going to be finding the equation of the line tangent to x plus y cubed equals x cubed plus y cubed and negative 1, 1. First thing that you need when you are finding a tangent line is a point. This problem is really nice because you actually got a point already. So you don't need to find the y value. Sometimes you just get the x value. I do want to point out that this thing, sometimes I get people writing it like x cubed plus y cubed. Please don't do that. You'll get a really weird answer. Just a side note. So let's go ahead and find our slope of our tangent line. Remember, you're finding slope of a tangent line by finding the derivative at that point. So let's go ahead. We're going to find the derivative with respect to x of this entire big long equation. So I'm just going to go ahead and write each term separately. Unfortunately, it's much more complicated if you write out the x plus y cubed. I don't recommend doing that. I think implicit differentiation is a little bit easier. However, implicit differentiation with that thing, there's definitely more opportunities to make mistakes. So I'm actually going to start with the right-hand side just because it's a little bit easier to deal with. So the derivative of x cubed with respect to x is just 3x squared. The derivative of y cubed with respect to x is 3y squared times dy dx. So to make this problem a little bit simpler to look at, I'm going to rewrite that. I'm going to write dy dx as y prime. You don't have to do that. You can write dy dx everywhere, but I think this just makes it easier for more complicated problems. So now let's work on that left side. The left side, you are going to use both the chain rule and implicit differentiation. There's quite a bit going on. So let's start by taking the derivative of our outside function. Derivative of our outside function is 3 times the stuff inside to the second power. Now I need to take the derivative of my inside function. The derivative of x with respect to x is just 1. The derivative of y with respect to x is just dy dx. So I end up getting y prime. So I actually didn't need as much room as I thought I would. This one isn't as bad as it looks. So now here's the hard part. You're probably going to want to solve for y prime. Now, a little trick on this one, if you do not want to do that, you can actually just substitute in -1 and 1, and you'll be able to get an answer from there, and it makes the problem a little bit easier. However, just for practice, I am going to solve for y prime. So first thing I'm going to do is use the distributive property on that left-hand side. I get 3 times x plus y squared plus y prime times 3 times x plus y squared again. You do not need to simplify that whole thing out, that x plus y squared. You don't need to FOIL it out. You can if you want, but it's not necessary. All we're trying to do right now is solve for y prime. Next thing I'm going to do to solve this out, I'm going to get all of my y primes on one side of my equation. So I'm going to move over this one to the right side, and I'm going to move over this one to the left side. So next step, I get 3y prime times x plus y squared minus 3y squared times y prime. This is equal to 3x squared minus 3 times x plus y squared. Again, don't simplify if you don't have to. The last thing I need to do in solving this out is I'm going to factor out a y prime. Actually, this is the second to last. Inside my parentheses, I get 3 times x plus y squared minus 3y squared is equal to that stuff on the right-hand side. My final answer for y prime, I'm almost out of room actually, is the stuff on the right side divided by the stuff on the left side. So this is my final answer for dy dx. It's pretty complicated, you can see. Occasionally you will have to solve things that are this complicated. So unfortunately, it's not something that I'm making it harder than what you're going to see on the AP exams. You probably will see something like this. However, the next part is not as bad as it looks. So we are going to plug in that point, -1, 1. Make sure that you plug in both the x and the y value for that point. And actually, a lot of stuff is going to cancel out. When you do that, you get y prime is equal to -1. You get a pretty nice answer. So then my final answer is my tangent line. Please don't forget to answer the question that they're actually giving you. You're finding the equation of the tangent line. You're not just finding the slope. I would recommend writing it in point slope form. It's a lot easier than doing it in slope intercept, but you've already done some hard stuff, so that's probably nothing compared to the stuff that you just did. So we get y minus 1 equals -1 times x plus 1. You can just leave it like that.